Okay, I wanted to just present this for those of you that are interested, and it's usually typically just a few people that are interested in this derivation, but it usually catches folks' attention when I mention that static friction, in the case of perfect rolling, static friction does zero work. And so I wanted to do a derivation of that and just show you that I can, talk about it conceptually, but we can also show that in a derivation, like show that why that must be the case. So I'll just go through that briefly. This is just a wheel. Let it like be a wheel and an axle, a bicycle wheel or something. It has some external force acting on it that's causing the rolling to happen, right? That piece doesn't matter as much. We're just focusing on the static frictional force here. So notice that static friction does negative translational work. That's the first thing that I say there. It's negative translational work. It opposes the translational displacement. So if I'm just looking at translation, I see that I have translational displacement to the right here. That's like the bicycle would be going to the right. And the force of static friction is to the left. So those are opposing. That means that the work done by static friction is going to be negative in that way. So interpreting that conceptually, a way you can think about it is this. If the wheel or the ball or however you're thinking about this were not spinning, if all the energy was just going into translation, say, then it would be moving faster, okay, with the same force on it. That's the way you can think about it. So you can think about the fact that the turning that it's doing, that energy has to come from somewhere, right? So you can consider that there's work being done on the situation by this applied force F here. That applied force F would be able to, in a translational way, accelerate the object more were the object not turning, if it was simply sliding. Okay, so that's a way to sort of like take in like how is this negative translational work? It impedes the translational acceleration or the gain in translational kinetic energy. Yeah. So this kind of goes back to work kinetic energy theorem here. But if you're looking at rotation, so that static friction does actually positive rotational work. So, and that, might make more sense that really the reason that there is any rotational kinetic energy at all in this situation is because of that force of static friction. And if you want to work that out, you can just do that. And I lead you through that here, where we're using rotational variables here, rotational quantities instead of translational. So if I look at the rotational work done, this equation, instead of looking at the scalar product of force and displacement, I'm now looking at the scalar product of torque and angular displacement. But it's going to give me the same thing. So I can figure out what that is. In this particular case, both the torque and the angular displacement are into the page, so they're aligned. And this is going to give me positive work. So positive work done by static friction here in the rotational realm. So the total work that's done on the wheel then is due only to that applied force F, not the static force of friction at all. So when I sum up all the works, right, done by static friction, I see that they're actually equal and opposite. It's kind of interesting there. Okay, so feel free if you need to like work through that on your own, you really want to see it. This generally tends to be just for motivated students that really want to kind of get into this and get a feeling for why this is. And then it's kind of worth looking at. You can look at it in a couple different situations too. You can look at it if you want to if you're interested in this derivation, you can look at the derivation for, you could think about the same thing happening and ask yourself this kind of interesting challenge question. How would this be different if it were on an incline?